We've now talked about 4 families of algorithms. One of them I wouldn't really call adaptive, but that's the least squares approach. And the idea with least squares is that we solve the normal equation, or the Wiener-Hoff equation, and we have to use Rx, either estimated from the data or expectation. We rarely have the expectation data available. Or from a database estimate. And RDX. Okay, this gives us something where we can just jump directly to our solution. So if we have this situation where we have 2 weights, because that's all we can easily plot, if that is the optimal solution right there, then least squares picks it out. Okay, next is least squares via a gradient. And it gets to, it's essentially solving the least squares equation and it goes directly there, if you will, using many steps. Then we came up with the LMS algorithm, and this was also a gradient search, but using a noisy gradient. The gradient least squares approach used Rx and RDX from the least squares solution. Here we have noisy gradients based on, it's almost hard to call it an estimate of Rx and RDX, but based on instantaneous values. So this one is going to do something like that. It's not nearly as pretty. Then we have RLS. So what is RLS doing? Making our gradient one still visible under this mess that is RLS, or LMS. RLS is going to show up eventually with our correct estimate, but it's not going to track in exactly the same way. It might quickly get there from some other point, and the reason why is it's choosing the best solution based on all available data. So in a sense, this is optimal based on data seen, so talking about it getting to the correct solution has to be thrown into a different context. If, for example, we were doing system identification with RLS, it will get to the correct solution and it will get there very quickly. But every step along the way is optimal based on the data that it is seen. Okay, so convergence then is it's it instantly converges to the best solution given the data so far. Okay, I've copied some code here that implements the RLS algorithm, and let's walk through that line by line, if you will. Okay, so this is a MATLAB function, and the inputs are the data to your adaptive filter, your target or desired input, and ORD is the number of filter coefficients, the order of your filter. Lambda is our forgetting factor that we've labeled lambda, and delta is what we use for our initialization of Rx. It's a small number. The outputs are the error signal and our final weight vector. We have down here just a summary in the comments of what our adaptive filter is doing. So we're using the alternative form that pre-computes Pn-1 times x to make things a little bit simpler. If we don't specify the delta used to initialize our Rx of 0, then it chooses 0.001. So that gives you an idea of something that might be typical. One over delta is our P, and then we initialize our weights and our error to zeros. Okay, now let's see. This little step here, x is equal to zeros at x, we're essentially prepending a bunch of zeros onto x. This makes the indexing easier later. So when we look at previous values of x, there actually are previous values of x for us to loop back through. So this right here then is our creation of x of n. So one thing that we did not show before is everything that we did was real, and this one actually handles the complex case as well. Because of that, we have the conjugate of x here. So for complex filters and input, we want that to be conjugated. Next, we create g is equal to z divided by lambda plus x transpose times z. In MATLAB, the dot followed by the single quotation mark is a transpose, whereas the single quotation mark alone is the conjugate transpose. So we do our weight update, our update of P. Once we've done our weight update, we can calculate the filter output, d hat. We get our error, our posteriori error, and actually if we have more arguments at the output, then we also compute our history of the weights so we can watch how they track. Okay, we've looked at the code. Now to compare these two in operation, I've set up a system identification scenario where we have X coming in. It goes into some unknown filter that for us we've labeled H. And then we go into our adaptive filter, and as you've seen before, this would be our desired signal, our error output, and the adaptation of our weights. So over on the left, we're going to run this filter for 200 time samples, and the order of our filter is going to be the unknown filter is of length 10, but we're going to pretend we don't know that, and we're actually going to create a W of length 20 to make sure that we capture that. Here we have lambda is 0.95, and 0.01 is the delta that we're going to use to initialize Rx. Similarly, we're going to run an NLMS filter. The NLMS filter is going to use a beta of 1/2, so that's somewhat aggressive. And here are the results of this thing. We've plotted the weights in blue and the estimated weights over top of them in red, and you can see that for the RLS they're overlaying exactly. You can't see the blue underneath. Whereas with the NLMS it didn't quite get there yet, but it's close. The error, we have no additional error on our D, so we would expect the error to go to 0. And you can see that it goes to 0 rather quickly. Let's see, so if that's 50, that's about 25. It looks like it's pretty near 0 by the time we've hit 10 samples. In other words, by the time we've had enough samples to look through the entire filter, or characterize the entire unknown filter, we have almost perfectly characterized it. It's not perfect. I don't know if you can see, but there's a little bump right there. But it settles down by the time we're at 50. The error appears to be at 0. Whereas even with our aggressive NLMS filter, the scales are different. And so maybe that's an issue here. Oh, and that's a log plot. I might just go ahead and recopy that using the same scale so we can compare. Okay, through the magic of pausing the video, we now have two things that are moving along very similarly. We still have the scale on the left axis different than the one on the right, but that's because the error performance is such on the left that it would be off the charts if you wouldn't be able to see it if we scaled it the same. But they're both linear in this case, and so now that we can see that it takes substantially more samples for the error to get close to 0. And so the RLS filter does system identification much, much faster.